Hello everyone, we're Group 2K and we would like to share with you our exam question for this presentation. Our plan is to set up the problem and show key steps, but we will not provide the full solution. Today, there is growing demand for environmentally friendly gas turbines. Fuel efficient and low emission gas turbines incorporate a heat exchanger in them. One type of heat exchanger in this application is an annular recuperator, which uses exhaust air to heat incoming compressed air before combustion. This is especially attractable for companies who want to commit to fuel saving cost. As shown in the figures, air flows to the compressor to the recuperator, then is combusted in the combustion chamber. Exhaust air rebounds from the housing to the recuperator again and out the exhaust outlet. It is desired to study the temperature distribution and heat flux of this system. The recuperator is made of aluminum nitride with an thermal conductivity of 180 watts per meter degree Celsius. Hot air enters the recuperator at 600 degrees Celsius and exits at 200 degrees Celsius before exiting to the exhaust outlet. The recuperator is 15 centimeters in length. Assume laminar flow for this problem and that the recuperator is a continuous solid. Determine the following. Draw a shell energy balance on the recuperator. Determine the temperature distribution in the annular recuperator. Sketch the temperature distribution profile of the annular recuperator. Determine the heat flux to the annular recuperator. Obtain an expression for the average temperature over the area of the annular surface. Explain why might a shell energy balance is not best appropriate in solving problems in these applications. We'll start off by drawing the shell balance in the recuperator. The recuperator is assumed to be a continuous solid, meaning no holes or gaps. So we can imagine it as a discontinuous solid cylindrical block with a hole in the middle. We situate the coordinate axis on the right side in the middle. Then we assume heat conduction in one direction, which is in the axial direction, and from this we're able to draw our shell balance. What's remaining is the energy flows to the wall, or shell. Asked to determine the temperature distribution in the annular recuperator. So the first step is to outline any additional assumptions to the ones provided in the problem. That is, assume steady-state uniform heat conduction in the z direction only. So the next step is to write out the shell energy balance equation and cancel out terms like the rate of energy production by sources, since there is no resistive heating or chemical reactions, as well as the rate of work done by gravity, because there is no mass of fluid flowing within the recuperator or our shell balance. Then once you write out and simplify your energy balance equation, you should get equation 1. That's when you write out the combined energy flux equation and do some more simplification. So for instance, the first two terms in equation 2 cancel because there is no bulk fluid velocity within the control volume. And this means that the only energy transfer in this problem is by Fourier's law of conduction. So when you substitute equation 2 into 1 and do some more substitution in math, you should end up with equation 3. Now you write the two boundary conditions provided in the question. At each side of the recuperator, you're given the temperature, which you substitute in equation 3 to solve for C1 and C2. Then you will end up with the temperature distribution. The question asks for the temperature distribution profile in the annular recuperator. So since the temperature distribution we found in the previous question is linear, then the profile should look something like this from the side view. Next question asks to find the heat flux to the recuperator. So from the second question, in one of the steps, we obtain the expression C1 equal to minus K times dt over dz. So you're given K, the temperatures on each side, as well as the length. Hence, you should get 480 kilowatts per meter squared. Great. So now the next question asks to obtain an expression for the average temperature over the area of the annular surface. So basically, you take the double integral of the temperature distribution you found previously over the double integral of the area of the annular surface. So be careful not to get mixed up with cross-sectional area. Now, after some lengthy integration, you should get the average temperature of 467 degrees Celsius. Finally, the last question is conceptual. So why wouldn't the shell energy balance approach be appropriate for solving problems in these applications? Well, firstly, in gas turbines, air is typically turbulent. Shell energy balances are only appropriate for laminar flow problems. The problem analyzed the recuperator as a continuous solid. A recuperator consists of hundreds of air cells, which are fabricated by thin folded steel sheets. A more suitable approach would be to analyze the temperature distribution of a single fin. And thirdly, the shell energy balance only looked at heat conduction in the Z direction. However, in reality, temperature varies in the R direction as well. And that concludes our presentation. Thank you.